Before we start looking into algorithms for aligning biological sequences, it's best to take an overview of dynamic programming. This is a general approach to optimization problems that have these characteristics. They have an optimal substructure, so basically we can decompose them into sub-problems and optimize those sub-problems. And there is this sub-problem overlap, which means that these different sub-problems may lead to computing the same answer many times, and we can find ways of doing that more efficiently. We're going to look a bit at these characteristics and the approach of dynamic programming, and this is important before looking at sequence alignment, because sequence alignment algorithms use this approach. We're going to start with some simple examples. I'm going to focus mostly on the Fibonacci series, and we're going to start looking at a recursive solution. Usually this is very intuitive to understand by the way the problem is formulated, and memoization as a method to reduce the time it takes to compute the solution by avoiding the need to recompute solutions to sub-problems. Then we're going to go a bit beyond this into a more efficient way of designing these algorithms, where we have a bottom-up approach. Instead of using this recursive solution from the top down, by using this bottom-up approach, we can if we understand the right order for solving these sub-problems, we can create a more efficient table of the intermediate results we need to keep. So, and this approach that we're going to see at the end is what is meant usually by dynamic programming in a strict sense. So we can consider that all of this is dynamic programming in a broader sense, but many authors just reserve that term dynamic programming for this last more efficient way of solving the problems. But we're going to do this step by step so that you understand the idea. So let's start with dynamic programming, the basic idea and what kind of problems we can solve. This expression, dynamic programming, has a curious history beginning. It was coined by Richard Bellman in the context of planning, of research, mathematical research into planning. So ways of optimizing sequences of procedures in order to optimize something about the plan, say the time it takes to complete or the resources that are used and so on. As Bellman tells, at least in this version of the story, in 1950, the Secretary of Defense at the time had some strong aversion to mathematics and research and so on. So Bellman had to figure out some way of labeling his research into planning in a way that didn't use research or mathematics or planning or things like that. So he used this expression of dynamic programming. So programming in the sense that it was to program some plan, a series of steps to be undertaken, and dynamic as a reference to the time dependency and the way the plan would fit together along the time, and also because he thought it was impossible to use the word dynamic in a negative sense, in a pejorative sense. So this was the origin of the term. It also has a parallel with other branches of mathematics like linear programming. So it says the same idea of solving these optimization problems in a specific way. So in the case of dynamic programming, we have this method for a category of optimization problems. So one of the characteristics that the problem must have in order for us to use dynamic programming is this optimal substructure. The idea here is that the problem has an optimal substructure if the optimal solution to the whole problem also includes optimal solutions to parts of the problem, to sub-problems. One example is if you're trying to make change. So suppose we want to make change for 58 cents. You need to give your client 58 cents in change. And you want to minimize the number of coins you're going to give. So let's suppose that the best solution includes giving a 5 cents coin. If the best solution includes giving a 5 cents coin, then it will also include the best solution for 53 cents, which is the same as 58 minus 5. So we could decompose the problem in giving 5 cents to the client and then optimizing the 53 cents change problem. In general, if we are going to use coin C, then we need to optimize the solution for the change of M minus C, where M is the number of units we started from. So since this is the case for making change, this problem has an optimal substructure. We know that if we solve the optimal, we find the optimal solution for the 53 cents change, then we can use the additional 5 cents coin. And if this one is better than using any other coin, then we have the solution for the whole problem. We will not need to go find other solutions for the sub-problem of doing the 53 cents change. So if a problem has this kind of structure, this optimal substructure, we can solve the larger problem by solving smaller sub-problems. So one algorithm for this could be, we have several different coins. We could test each different coin and see if the remaining problem can be solved with fewer coins. And then we could choose the one that gives us the lowest total of coins. Another attribute that a problem must have for dynamic programming to improve the efficiency with which we solve it is this sub-problem overlap. The idea is that when we are trying to solve by looking at all the different sub-problems and the different solutions, we find the same sub-problem over and over again, several times. For example, suppose that we are checking to see how could we make the change for 58 cents with the smallest number of coins. We could start by checking if we use a 2-cent coin and then see how many coins we're going to need to make the 56 cents change, which is what is left over after we give these 2 cents. We could also test with a 1-cent coin. This would give us a problem of making the change for 57 cents with the smallest number of coins. But when we are trying to solve this problem, we would again find the 56 cents problem that we had in this case, because if we are now going to check with another 1-cent coin, we're going to fall into the same problem here. So if we find the same problem in different branches as we search for the best solution, then we have this sub-problem overlap, and this is a problem for the efficiency of the algorithm. Okay, so let's look at a simple example where we can see this in more detail to better understand these problems. So in order to find these optimal solutions, we are going to use these sub-problems and then compute the final solution for these problems. This is this approach of this characteristic of having this optimal structure in the sub-problems. And we also need to avoid repeating the computations. So these are the two characteristics we want for the problems in order to solve them with dynamic programming. So in the case of the coins, we have this approach here. To find the minimum number of coins for change for some number of monetary units, we can use this top-down approach of decomposing the problem into choosing one coin, maybe 1 cent, 2 cents, 5 cents, and so on, and then solving what remains, which is making change for the total number of units minus the coin that we chose. So if we search through all these possible coins and count how many coins total we need, we can choose the best option for minimizing the number of coins. And so, but one problem here is that as we are testing all these different combinations, we are going to revisit over and over again some specific numbers for this M value. And so if we store each time we compute how many coins we need for change for some number, 58 cents, 56 cents, things like that, every time we meet this problem again, we can just remember it. The idea here to understand this is that this is a general approach. Note that this description here is not itself an algorithm. You cannot tell the computer, give an algorithm to solve any problem by dynamic programming, because this is just a general idea, a pattern that we follow to find the solutions. So it's a method for solving these problems, but then we use that to think about the algorithms we are going to use to solve each particular problem. Also note that this is not something that you can apply to all problems. You need to have this optimal substructure in order to be able to break down the problem so that you can find the optimal solution by finding the optimal solution to the subproblems. In some cases, this is not possible. For example, imagine that you're going to visit a set of cities traveling by airplane. Sometimes it happens that if you want a direct flight from city A to city B, it's actually more expensive than going with a connection flight from city A to C and then from C to B. So if you want to find the cheapest combination of flights to visit a set of cities, you cannot guarantee that you can solve this by looking at subsets of smaller subsets of the cities, because it may actually be more expensive to visit fewer cities than to visit more cities, because of the problem of connecting flights, because you can have discounts if you travel more than a certain number of kilometers, and so on. So this problem would not have that optimal substructure, and you cannot solve a problem like this with dynamic programming, because you cannot break down into subproblems and guarantee that finding the optimum for each subproblem will put you on the right track to finding the optimum for the complete problem. But let's look at a simple example where we can illustrate these problems and actually create the algorithms explicitly, so you see how are the algorithms we can create using this dynamic programming approach. We're going to look at Fibonacci numbers, and the series of Fibonacci numbers starts at 0. So the Fibonacci number of index 0 is 0. The Fibonacci number of index 1 is 1. And then each number is the sum of the previous two. So we start 0, 1, and then it's 1 because it's 0 plus 1. Then we have 2 because it's 1 plus 1. 3 is 1 plus 2, and so on. And so the number keeps increasing as we go along the series. Now, if we wanted to implement an algorithm to compute this, it's very easy just to follow the structure of this mathematical definition. So we have these terminal cases, 0 and 1, and then we have a recursive definition for the Fibonacci numbers, and we can just implement that simply. So let's say this is our algorithm. We have this function fn for computing the Fibonacci number of index n, and we check if n is less than 2, that is, if it's 1 or 0, then we simply return n, because f1 is 1 and f0 is 0. This takes care of these terminal cases here. Otherwise, if it's not less than 2, so if it's 2 or more, then we return the sum of fn minus 1 and fn minus 2. So basically we are calling again the same function, and we are doing this computation. Now the way this works is that, for example, if we have n2, we skip this condition, it's not less than 2. So now we have to sum f of 1 with f of 0. And each of these will call our own function again. So f of 1 will call here and return 1. F of 0 will also fall here and return 0. So then we have 0 plus 1 and we compute f2. If we have f3, for example, here, then we are going to call f2 and f1, and we are going to call the same algorithm, the same function, several times until we get our computations. So we can look at this as a tree. Each of these calls will create a branch in the tree by calling the different fn-1 and fn-2. Let's suppose we want to compute f6. To compute f6, we will call the function f for the Fibonacci numbers for n-1. So if n is 6, we'll call it for 5 and 4. So we create these two branches. This instruction here will create these two branches asking to compute Fibonacci of 5 and of 4. The 5 will call 4 and 3 because it's -1 and -2. 3 will call 2 and 1, but I'm omitting 1 here because 1 will actually not do any computation. It will just look up the value and return it. But f2 will do the computation and so on. And as you can see here, this branch that's going to compute f5 and then f4, f3, f2 also is going to repeat these computations. For example, f4 is also going to be computed on the other branch. When we compute f4, we need to compute f3 and f2, and this will happen here and also on the second branch when we are computing f5. So we are computing f4 twice, f3 3 times, and f2 5 times. And as you can see, this is why our solution is inefficient, because we have this subproblem overlap. As we visit the different branches, we fall repeatedly into the same subproblems. And if we keep computing them, as we keep increasing n, this tree will grow exponentially, and at some point our whole algorithm becomes useless. So one way of solving this, which would be quite intuitive, is if you're going on this branch and we compute f5, then we store the result. After computing f5, we store the result somewhere. Of course, to compute f5, we need first to compute f4. Before that, we need to compute f3. And before that, we need to compute f2. So you can imagine, as we go here on this function, we call f6. This condition is false, so this is ignored. And our function will now call f5 and wait for the result until adding to f4. So basically what we are doing is, when we want to compute f6, we are going to reach this point where we ask for f5. When we want to compute f5, because now f6 is waiting until f5 finishes computing, when we're going to compute f5, we'll fall here again, but this time calling f4 and then f3 and f2. f2, when we call for f1 and f0, then this immediately finds the values 0 and 1, returns them. So f2 is quickly to compute, and then it goes back again for all these calls and adding the other branch. So in the case of f3, the other branch is f1. We don't need to compute anything because f1 we know is 1. But then for f4, the other branch is f2, and so on. So if each time we compute one of these, we store it, we can skip all the repeated computations that we are doing on that tree. So let's look at the algorithm for using memoization. This is the idea here is that we're going to store intermediate results and reuse them whenever we need. One side note, I'm going to implement this algorithm by decomposing into several parts. So this is the whole thing to compute the Fibonacci number of index n, this capital N. So we're going to start by creating an array, let's call it memo, with this number of elements, and all of them set to -1, because we still did not compute. So this array will represent f2, f3, f4, and so forth. We did not compute them yet, so we are setting everything to -1 to signal that we don't have the values yet. And now what we want to do is we define our function fn for the Fibonacci numbers. We have the same thing. If n is 0, we return 0. If n is 1, we return 1. Or alternatively, we can say if n is less than 2, we return n. This is the same thing, but basically these are the terminal cases. If n is greater, then we're going to check if we already have the fn-1 and fn-2 computed. And to do that, I'm going to decompose this into two different functions, and this one just does that check and does the computation if necessary. So how do we do this? If we need, for example, here, we're going to need f5, and then f4, f3, and so on. This will check if the value for this n in our memory array, is smaller than 0. If it is, it means we did not compute that yet. So we are going to store in our array, in that position n, the result of doing the computation for the Fibonacci number n. So, and in the first time, this will try to compute f5. And as it tries to compute f5, it will call f4 and f3, and then f2, and so on. So, and each time it calls one of these, it will store it in the array. After storing, it will return the value in the array. So the idea here is that we only compute if we don't have it there, and in that case we'll store it in the array. But then we simply return the value that is in the array. So if it's already in the array, we don't call any computation, we just return the value in the array. So what this does is that it reduces our tree, and we get only this line of actual computations, because when we start here with n equals 6 and we need to compute the Fibonacci number of 5 and 4, we're going to call the computations for 5 and 4. This will call the computations for 4, 3, 2, and so on. All of these will be stored in the array. But then when we need to call again 4 on this other branch, we don't actually need to compute, because this check function will find it in the array and just return the value that was previously computed. So we avoid all these repetitions, and we only compute each of these Fibonacci numbers once. We don't have to do it twice, 3 times, and so on. So this is memoization. We are going again from the top down by using this recursive algorithm. But at each point we check if we already have that value for that sub-problem computed. If we don't, we compute it and store it, but if we have it in store in our memory, we just look it up, and so we save time in these computations. Okay, so now there is another approach that we can follow here. So far we've been looking at things from the top down. That is, we start from the largest problem, for example, computing the Fibonacci of 6, or trying to figure out the number of coins we need for the whole change that we have to make. And then we go down into sub-problems. We use that recurrent definition of the problem, and we step down into smaller and smaller problems. And with memoization, we are going to check if we have the values already stored, and if we don't, we compute them. If we have them, then we reuse them. But we are going to check and store in the order that we end up following during this recursion. Now the question is if we can do better than this. And in this case, we can, if we find the right order in which to solve the sub-problems, we can start from the simplest ones and then store only what we need for the next problems. So look at this top-down approach in this case, using this recursive function where we call the solution for the smaller subproblems and go down this tree. So we start from the top and go down. We are memorizing all the Fibonacci numbers in this array because we are going to need them several times, so we need to store them all in memory and keep them all in memory as we are moving down into simpler and simpler problems. But we can do this in the different direction by noticing that we only need the two last Fibonacci values to compute the next one. So if we start, if we create a function that starts from the first two, 0 and 1, and then just computes the next Fibonacci number by adding the previous two, and then updates this, always retains the previous two numbers, we can compute the Fibonacci numbers going from the first to the last in the series, in the part of the series that we want, without having to store every intermediate value. We only need to keep track of two of them. So in this case, I actually wrote the algorithm in Python. This is probably still not very familiar to you, but it doesn't matter. In these first weeks and the first exercises we're going to do, you can use whatever language you want to specify the algorithms. We're not going to worry about the formalities of specifying the code. Just remember that you have to give all the details so that it is an algorithm. But we're not going to worry about the syntax and the language. But in this case, I took this excuse that I have to show this algorithm, so I already will show you how it looks like in Python. And the idea is we are computing again the Fibonacci number of index n. We are defining this function that does this. This is no longer a recursive function. We are not calling the same function inside the function in order to move down from the last problem to the smallest subproblem. Rather, we're going to do it iteratively, starting from the beginning. So first we just check if we are in the first two Fibonacci numbers. So if it's 0 or 1, we just return that number because these are just the first two numbers in the series. If not, then we are going to start by pointing our previous number to 0 and our current number to 1. And now, if we have to go over a number of times, so if we have to step, for example, to 6, we're going to repeat this computation of adding these numbers in order to find the next one in the sequence. And the number of times we're going to repeat, we can do it like this. As long as n is greater than 1, we are going to do the computation and reduce n by 1. And the computation that we're going to do is adding up these two values, the previous one and the current one. We're going to put that in the new current one. So the new current one is going to be the sum of these two. And the old current one is going to go into the previous one that we had. So you can do this in Python in one single line to avoid the problem of needing another variable just to store things temporarily. Because if we are changing this value here and changing this one also, either we do everything at the same time or otherwise this will give us an incorrect result. So in this way, you can do it in one single instruction, and this tells Python to first compute everything here, and then store these things in the variables. Okay, so let's look at what happens when we call this with F6. This condition is false. 6 is not smaller than 2, so this part is ignored, and we start with a previous of 0, a current of 1, and an n of 6. So we enter here and we're going to update this. Previous plus current is 1, and this is going to go into our current variable. And the old current variable is going to go into previous. So now previous is 1 and current is 1. And n is going to decrease and it's 5. And now we're going to do this again because n is still greater than 1. So now we have this previous will retain a copy of current, but the current will retain the sum of the previous and the current. So we update this one to be the sum of the two previous values, and now it's 2. And we also copy the old current into the new previous one. So this way we're always keeping track of f at the current position that we are in the series, and the Fibonacci number on the previous position on the series. And now we do this again, and the sum of these two is now 3. Now we copy this one into the previous. Now the sum of the two is 8. We copy this one into the previous, and so on. And note that now we don't need to store an arbitrary number of Fibonacci numbers all along the sequence. We only need this very small table with the two numbers that we need, which are the current one and the previous one. And from that we can compute the next. And we just need to do this as many times as necessary in order to get the Fibonacci number. So one simple way of doing this is just to count down on the n until n reaches a small number, or we could just do here a for loop, which we can do this in Python, which would be something like this. We would just iterate a number of times equal to how many steps we still need to reach the end. So in this case, we would still need 5 steps in order to reach the end result. And when we reach the end, we have in the current variable the Fibonacci number that we want. Okay, so this is a bottom-up approach, because instead of starting from the last problem here, the biggest problem, and then recursively calling the function to solve the smaller problems, we are starting from the bottom, from the simplest part, and then building up until we reach the end, the solution that we want. And if we do this in the right order, we can minimize the number of values we need to keep in store, because we can keep only those that we know we're going to need later on. Whereas when we do this top down with memoization, we need to store everything, because we may need all of these various values in different order. Okay, so to sum up, the idea is that dynamic programming is an approach to these kinds of problems that have optimal substructure. It means that finding the optimum for the large problem includes finding the optimum for the sub-problems, the smaller problems. So we can break things down into smaller sub-problems, compute the optimal solutions for the smaller ones, and then add everything together or combine everything together to get the optimal solution for the largest problems. Also, they have this characteristic of having overlapping sub-problems. You can find a problem that has optimal substructure, but there is no overlapping sub-problems. So if it's something that is naturally like this, then there is no point in using dynamic programming, because you don't gain anything. If the problem itself is already a single straight line, you don't gain anything with dynamic programming. But when it's not, when you need to make it so that you don't have to repeat all the computations, so in the case that it has these overlapping sub-problems, then you benefit a lot by using dynamic programming, because you identify what you need to retain in order to avoid having to repeat all the computations. For example, here in the Fibonacci numbers, because we always keep the previous one in memory, then when we need to compute the next one by adding these two, we don't need to recompute the previous value. We already remember what it was, and so we save time there. Or if we are doing it top down, then we can simply store all the values we compute, and every time we need them again, we check our memory for that. So this top-down approach that we saw first can be more intuitive. When we have these problems with an optimal substructure, typically the recursive solution is quite obvious, because we can think about how to reduce the problem a bit. For example, in the problem of making change with the smallest number of coins, it's very intuitive that if we pick a coin, then we reduce our problem to just making change with the remainder after we remove this coin. So we can easily think of the problem top down by looking at the whole problem and how we can shrink it a bit by taking one step. And this leads to memoization to avoid repeating the computations, but we can make things more efficient by going bottom up. And generally, in a strict sense, many authors use dynamic programming just to refer to this approach of going from the simplest problem to the complete problem that we want to solve, and using tabulation instead of memoization. The idea is that in tabulation, we know in advance which values we're going to need, so we only need to store those that we're going to need later on. Whereas memoization simply starts keeping track of everything in case we need it in the future. Okay, so this is the idea, and this will be important in the next lecture for sequence alignment, because the alignment of biological sequences, the algorithms take advantage of this approach in order to optimize, to find the optimal alignment between sequences.